In section 3, we're going on to multiplying radical expressions, some of the basic rules. Now, notice if we say the square root of 4 times the square root of 9, square root of 4 is 2, square root of 9 is 3, 2 times 3 is 6. Now notice, since this is both square root, our index number is 2. If we put them under a common radical sign, we have 4 times 6 is 36, and the square root of 36 is 6. So what we're showing here is that this is equivalent to this and can be used to multiply radical expressions, as long as the index numbers are the same. And that's what they're illustrating here with this rule. Now notice we could also have converted them to fractional exponents that we had in the previous section, and the results are the same. So as we do these, what do we note? Well, again, theoretically what you would do is put these under a common radical sign and get the square root of 30. But we can do this step mentally. And for this would be the third root of 9 times 7 is 63. And for this one, it would be the fourth root of 5x over 3c. Now again, the product rule only applies if the index number is the same. So they're saying here you can't do this. You can't do this because the index numbers are not the same. All right, you can look over this rule here. And I will illustrate this in the next example. So if you have the index number and then a product, what they're saying is you can separate this product into their factors. And if one of these factors is a perfect square, you can factor that out. So here's what we'll be doing. And you can read this over. And I will illustrate it in the next few slides. To keep the tape short, I'll continue, but you can pause it if you want to read it. And here we're assuming that it was not a negative number if the index number is even, because those would be not real numbers. Okay, so let's look for a strategy here of what we need to do. Now, what we should be thinking of in our creative mind's eye, so to speak, we're going to put two radical signs with the same index number. Now as we look at this radicand, is there some factor, think of it as A times B, is there some factor that is a perfect square? And you might say, yes, 100. 100 is a perfect square factor of 300, and you're left then with a 3. So if you were to multiply these, you'd get that, but we're trying to simplify, and we're saying we could factor 300 into 100 times 3. Now, what is the square root of 100? And the answer is 10, the square root of 3. So we have simplified 300, going through two radical signs, putting a perfect square under one, the largest perfect square, and then the other part that's not, and then taking the square root of that. So again, let's work this technique for this one. Now, as we look at the product 8, is there a perfect square factor in 8? And the answer is yes, 4. And then the other part that's not a perfect square is 2. Now as we look at m to the 4th, is that a perfect square? And the answer is yes, because it's an even exponent. And then n is not a perfect square. So now we take the square root of this, which is going to be 2m to the 2nd, and then the square root of 2n. So what we're doing is reversing what we had done earlier so that we can simplify these radicals. Now this one, note, is a third root. So our technique is to put two radical signs, each with the same index number. And now we're looking, is there a perfect cube factor in 54? Well, if we divide 54 by 2, we get 27, which is a perfect cube, and then 2. And in s to the 4th, what would be the perfect cube? S to the 3rd. And what's left is s. So now we take the cube root of this, which is 3s, and what's left is this. So what we've done is taken these products, divided them into perfect whatever we're looking for, squares or cubes, and then whatever's left, take the actual root of these, and then what's left. Okay? There's the first one, and there's our answer. And the second one, again, they're using a little different technique, just dividing it up. I like to put it already into the way I did it, but again, there are other ways. See, rather than do this step, I go right to this step. And there's the answer. Okay, so here is something now in function notation. And we want to simplify that. Okay? Now notice you can see that this can be factored by 2, but let's watch them do it. So they factor this by 2, and they get this. And do you recognize what's here? This is a perfect square trinomial that will factor into this. Okay? So taking the square root of this will just give you this part outside of the radical, and we can put that in their absolute value form. And then what's left under the radical sign would be the 2. So this, simplified, ends up as this. And if we check it, it looks like that, using your graphing calculator. We'll let you read this. Again, if you want to pause it. Now, as we look at letter A, keep in mind you might have thought of it this way. 2 times 5 times 2 times 3. So there's 10, there's 6. And now I'm going to use the commutative property that we studied a long time ago and put my 2 times 2 first, and then my 3 times 5 perhaps. Now what is this? Well, this is 4. So I have the square root of 4 times the square root of 15. And now I take the square root of 4 and get 2 the square root of 15. So it started off, and again I would have done it maybe a different way, but I wanted to show you what's going on. Now for letter B, let's do what we've done here. So on this first one, we'll put it all under one big one here. So this is going to be 3 times 3, x to the third, y to the second, and then this is going to be 3 times 3, x to the fourth, y to the seventh. So let's get all our perfect cubes under one radical, and then whatever's left over we'll put under the other radical. So I have 1, 2, 3. That's going to be 27. And then there's 1, 3 left over. Then I have x to the third, x to the fourth, which is x to the seventh. I'm going to go x to the sixth here. That's a perfect cube. And I have an x left over there. Then I have y to the second and seventh, y to the ninth. That's a perfect cube. So, taking all of these, I kind of teased them apart into their factors and then picked out those that were perfect cubes under one radical sign, whatever's left over. So, cube root of 27 is 3. I'm going to divide this 6 by 3 and get x to the second. 9 divided by 3 is that, and then the third root of 3x. And what we're trying to show here is a technique, a strategy for doing these. And that's what I've laid out. And again, if you had just multiplied them, you would have gotten 60, and then 4 times 15, and then take the square root of 4, get 2, the square root of 15. And this one, you would have gotten this, and then out of that is 27 times 3, which is what I believe they're going to show you. These are perfect cubes. and then what is left over is what we did. So perfect cube, perfect cube, perfect cube, and what's left over. Again, slightly different technique. The answer comes out the same. And that wraps up this section.